Hey folks, this is Heath. We are starting this section on error correcting codes today. This is day 10. This is a reminder that there is a web work assignment that is up today. This is web work number 3. And it's due on Monday. So what is Monday the 20? I don't know where that came from. Monday's the 22nd. The other thing I want to mention is if you go to today's news, vtnews.vt.edu, there's an article in this morning's news on two Virginia Tech alumni who were on a team of people who broke one of the Zodiac Killer's codes recently. And the article goes into a fair amount of detail about how the code was broken, and you'll recognize a lot of the terms from this class. They tried substitution codes. They tried the transposition codes, which we've both done. They tried hill climbing algorithms, which we've done. You know, if you read through the kinds of things that they were doing, you'll find that they went through a checklist of sort of a lot of the things that we did through the course of the semester. At a much more grand scale. They did a computer simulation that went through over 500,000 different cases before they started to find any patterns at all. We don't have the computing resources necessarily to do what they did, but what they did is just a scaled up version of a lot of things we're doing, and so. I thought you might be interested in reading the details on how they broke the code. Let's go ahead and get started. Last time we saw the Huffman encoding. This is a compression algorithm, not encryption. And it's achieves the maximum possible compression among single characters and encodings. I would love to prove that, but it's a little bit involved to prove that. The length of a Huffman encoding tends to be very close to the entropy, and in fact has to follow within the interval in the entropy and 1 plus the entropy. And so, for example, if the entropy of a piece of text was 3.5, the length has to be at least 3.5, but can't be higher than 4.5. So the length turns out to be a pretty good approximation to the entropy in most cases, and it's never more than 1 away. Okay? So let's try an exercise here. Twinkle, twinkle, little star. Let's compute the entropy for the sampled text. We'll construct a Huffman tree for this text. Let's determine the length of that Huffman encoding. So we'll start with part 1. The entropy is the summation of the probability of each letter times the log base 2 of the probability of each letter, where X is in the set T, W, I, N, K, L, E, and I think S, A, R, I think is what it comes down to. Fairly large set here, okay? So let's sort of write down what's in here. We have an A, an E, an I, K, L, N, R, T, and W. There are 9 letters in this sample if I've counted this correctly. All right, so we go through the words twinkle. I'm going to go ahead and list these twice because the word twinkle shows up twice in K, L, E. And then the word little, L, I, T, T, L, E. And then finally the word star. Oh, there's also an S in here. So I'm going to STAR. All right. And there are a total of 7 plus 7 is 14. 14 plus 6 is 20. 24 letters total. And so the entropy is going to be 1 over 24 for the A times the log base 2 of 1 over 24 plus 3 over 24 for the E times the log base 2 of 3 over 24 plus 3 over 24 again times the log base 2 of 3 over 24 plus then for the K 2 over 24 log base 2 of 2 over 24. L shows up 4 times, 4 over 24 log base 2 of 4 over 24. N shows up twice, 2 over 24 log base 2 of 2 over 24. And then finally, the last 4 letters are S and T and W. T shows up 5 times. That's the most that we saw. And then W, 2 over 24, log base 2, 2 over 24. So for a 10 character actually sample set, we have 10 different terms that we have to add together. This is a lot to punch into your calculator by hand, but this is a pretty easy thing to automate if you just have a, explode the string into an array, sort the array, go through all the text, and index how many of every character there is. It's a pretty easy thing to do that way. So now that we have this same data here, let's see if I can separate it from the answer to part 1. How do we construct a Huffman tree for this text? Well, all right. So I have 3 letters that only show up once. The A and the R and the S from the word star all show up just one time. And the way that we start with the Huffman tree is we pick the 2 nodes with the smallest weights. Well, there are 3 nodes that are tied, and so we can break that tie arbitrarily. And so I'm just going to break them in alphabetical order. So I'll start with the A and the R. So A has a weight of 1. R has a weight of 1. They combine to give me a weight of 2. And then there'll be a 0 on the left and a 1 on the right. All right, so A and R are out of the picture now. So then S also has a weight of 1. There's nothing else that has a weight of 1, so I have to combine this with a 2. I could combine it with this 2 here, the parent of the A and the R, or I could combine it with an N and a W, because I have a 3-way tie for a 2, or the K. I have a 4-way tie for 2. The parent of A and R, and the K, and the N, and the W. Again, when you have a tie, you could break it arbitrarily. So I'm going to go ahead and combine it with the 2 that's built here. So that's going to put S on the left. S has a weight of 1. It will combine with this 2 to give me a node of weight 3. 0 on the left, 1 on the right. All right. So that takes care of S. So now I have a K and an N and a W. Again, I'm going to do this alphabetically. So I'm going to do K before N, or K before N and N before W. So K has a weight of 2, N has a weight of 2, and they combine to give me a weight of 4. All right. So now K and N are taken care of. I still have a W with a weight of 2, and it has to combine with something that has a weight of 3 because I have no like everything left with a weight of 2. So I have a 3-way tie with 3s, E and I, and then this node here that's a parent of S, A, and R, or parent of S and grandparent of A and R. So I'm going to go ahead and use this one here. So W only has a weight of 2, so it'll go on the left. And the 3 goes on the right. 0 and 1. And now this has a weight of 5. Okay. And W is taken care of. So now I have 2 more items with a weight of 3. That's the E and the I. So I'll break them alphabetically. Put E on the left, I on the right. And now they have a combined weight of 6. All right. I have 2 things with a weight of 4. This L and this parent here. So L has a weight of 4. Oh, I didn't label my 0s and 1s here. Let me do that. L has a weight of 4. It combines with this node with a weight of 4 to give me a total of 8. And then this gets me a 0. This gives me a 1. All right. The L is taken care of. I still have a T with a weight of 5, and then this parent with a weight of 5. Right? And so that gives me a combined weight of 10, 0, and 1. So I have 3 nodes left, 6, 8, and 10. The 6 and the 8 are the 2 smallest, and I've drawn them in the backwards order, but I'm going to go ahead and leave it that way. I'm going to just make this a 14 and put the 0 on this side and a 1 on this side. And then finally, the 10 and the 14 combine to give me a 24 with the 0 on the left and a 1 on the right. So I get my total encoding here. T showed up the most times, and it only takes 2 bits to encode a T, a 0 and then another 0. L showed up the next most times, 4 times, and it takes 3 bits to encode. 1, 1, 0. And then I think W takes 3 bits to encode. 0, 1, 0. Is that right? Let's see. What about E and I? 1, 0, 0, 1, 0, 1. And then some of the less frequent letters, A only showed up once, is 0, 1, 1, 1, 0. That has 5 bits in its encoding. Okay? So in step 3, we want to determine the length of the Huffman encoding for this text. So what we're going to do here is we're going to take our formula for H, and actually we want the absolute value of this. I said H, eta. Take the absolute value of this. And instead of using the natural logs, we use the number of bits that it takes to encode these things. And so the length in this case is going to be, for A, it's going to be 1 over 24 times 5. For B, not for B, for E, it's got to be 3 over 24 times 3, is it? All right, 1, 0, 0. And then for I, it's got to be 3 over 24 times 3. And then for K, where's K on here? No, there's a K in here somewhere, right there. That's 1, 0, 1, 0. That's 4. So that's going to be 2 over 24 times 4. Then L is going to be 1, 0, 1, 1, 0. 4 over 24 times 3. N is right down here. That's 2 over 24 times 4. R is down here, that's 5 down, so that's 1 over 24 times 5. S is 1 layer up from there, but that's just because I broke the tie that way. 1 over 24 times 4. T is 5 over 24 times 2. And finally, W is 2 over 24 times 3. Okay? And when you multiply all that out, you get the length of the Huffman encoding. Eta and L should be, again, very close to each other, and that's one way you can check your work. All right, so that's all review of what we did last time. Let's move on and try some new stuff. So the Hamming 7.4 code is an error correcting code that encrypts binary messages by adding 3 check bits to every 4 message bits. And so if I have an 8-bit byte, so if my plaintext has 8 bits in it, 0, 1, 1, 0, 1, 1, 0, 1, for example, it will take these 4 bits and encode them, but pad them out to a length of 7. And then it'll take these 4 bits and encode them, but pad them out to a length of 7. 2, 3, 4, 5, 6, 7. And so the plaintext is 8 bits. The encoded text is 14 bits as a result. This is not doing any encryption. It is only doing error correction here. So this is not an encryption scheme yet, but we are adding some error correction features in here. As a result of these 3 check bits, we're able to correct 1 error per block. And so in an 8-bit byte, we could correct a total of 2 errors, 1 error in the first 4 bits and 1 error in the second 4 bits. In general, a Hamming code takes whatever n bits of data and then adds check bits to produce r bits of data coming out. So this is the size of the output, this is the size of the input. Richard Hamming published the specifications for these in 1950. Richard Hamming worked in Bell Lab about the same time that Claude Shannon did. And so a lot of interesting research was coming out of those labs at that time. All right. So here's the structure of the Hamming block. The 4 message bits are not stored consecutively. They're stored in positions 3, 5, 6, and 7. And the reason is that if we write 3, 5, 6, and 7 in binary, we have 2 or more 1s in each of those values. 3 is 0, 1, 1, 5 is 1, 0, 1, 6 is 1, 1, 0, 7 is 1, 1, 1. We're skipping the positions that only have 1, 1 in their binary. So 1 is 0, 0, 1, 2 is 0, 1, 0, 4 is 1, 0, 0. Each of these 3 values only has a single 1 in it and has 2 zeros. And so we're skipping those for the message data, and we're using the single 1 values, the powers of 2, 1, 2, and 4, as our parity check bits. So one way of thinking about it is that the parity check bits are all a power of 2. This is 2 to the 0. This is 2 to the first. This is 2 squared. Or they're the bits that only have a single 1 when you write them out in binary. Either way. Okay? So let's try to encode a block of message here. We're going to encode the message 1001. So I'll go ahead and load 1001 into the message registers. And then here's how I'm going to do the check bits. For the bit that has a 1 in the third position in the units place, I'm going to look at the other bits that also have a 1 in the units bit. And I want to make sure that the total number of ones that we see is even. Okay? So right now I have 1, 0, 1. There are 2 1s and 1 0. And so I'm going to make this a 0 so that there are an even number of 1s. Okay? All right. So that's the idea. So that if I look at all of the positions that have a 1 for its third digit, then those have an even number of 1s. Okay? In other words, we want the total to be 0 mod 2. That's where the 0 comes from. And then we do the same thing for the other 2 bits. 2 has a 1 in its middle position. And if we look at all of the values that have a 1 in the middle position, that's 2, 3, 6, and 7. I want those to be 0 mod 2. So I already have a 1 and a 0 and a 1. And so I need this to be a 0 so that I have an even number of 1s and an even number of 0s. Okay. And then we'll do the same thing with the last digit. 1, 0, 0. We're going to look at all the other places that have 1 for its leading digit. And since I only have a 0 and a 0 and a 1 here, then to get an even number of 1s, I need to make this parity check bit a 1. Okay? All right. And so the message that I wanted to send was 1001, but the block that I'm going to send that has the check bits in it is 00111001. So it's got extra bits of information in there that we can use to correct the data. All right. We can automate this encoding by using the following matrix. So let's talk about what this matrix is. The bottom row is the representation of the number 1 in binary. And this is 2 in binary, and then this is 4 in binary. I thought there was a pattern here that I'm not remembering. I forgot what the pattern is. Okay. 1, 2, 4, 8, 9. This is 11, and this is 13, I think. 8 and 4 and 1. Yeah, I don't remember what the pattern is for this, but there's a matrix here that if we take this and we multiply it by, so this is a 7 by 4 matrix, 7 rows and 4 columns. So if we multiply it by a 4 by 1 matrix, in this case is 1001, what we will end up getting is a 7 by 1 matrix. And that will be the encoded version of what we want. So we can see how this is going to work. The top row is 1101 times 1001. 1 times 1 is 1, plus 0 plus 0 plus 1 gives me 0 again. 1 times 1 is 1, plus 0 plus 0 plus 1 gives me 0 again. 1 times 1 plus 0 plus 0 plus 0 is 1. 0 times 1 plus 0 plus 0 plus 1 is 1, and so on and so forth. We get a 0, and a 0, and a 1. And so we end up getting the same answer we would have otherwise. So this encoding can be automated by a matrix multiplication operation. Okay? That's the important thing here. I did that on the next slide. Look at that. So let's talk about what we do now to break this apart. So again, these 3 bits are parity bits, and these 4 bits are message. And so we know that the message is going to be 1001 if, and this is an if, there were no errors. But if there was an error, here's how we're going to fix this. This is our decoding matrix. It's a 3x7 matrix. We're going to multiply it by the 7x1 matrix that we received. In the example here, 0, 0, 1, 1, 0, 0, 1. And if we receive everything correctly, we're going to get all zeros. No error, no error, no error. If we get all zeros, then we know that the message was received correctly, and the message itself will be in these 4 message positions. Okay? On the other hand, if there was an error, the vector will give the location of that error in binary. So let's take this same message, 0, 0, 1, 1, 0, 0, 1, and pretend that the fifth bit, got mangled. Okay? So instead of getting 0, 0, 1, 1, 0, 0, 1, Bob got a 0, 0, 1, 0, 1. So this is the bad bit right there. So when we calculate this product of the decryption matrix with the vector we received, we get 1 times 0, 0 times 0, 1 times 1, that gives me 1, 0 times 1, 1 times 1 gives me another 1, 0 times 0, 1 times 1 gives me a third 1, which adds up to 1. So on and so forth. 0, 1, 1, 0, 0, 1, 1. So 0 times 0, 1 times 0, 1 times 1 is 1. 0 times 1, 0 times 1, 1 times 0, and then 1 times 1 a second time is 0. So we'll get a 0 there. And the bottom row, 0 plus 0 plus 0 plus 1 times 1, 1 times 1 again, 1 times 0, and then 1 times 1 a third time is 3 ones. And so that gives us 1, 0, 1. Well, that's not all zeros. 1, 0, 1 is the number 5 in binary. And so that tells me that the fifth bit is wrong and it needs to be corrected. Okay? All right, so that's the idea that how this works. There is an encryption matrix that takes a 4-bit string and turns it into a 7-bit string. And then there's a decryption matrix that takes the 7-bit string, converts it to a 3-bit string that tells us the location of any error. And it gives me 0 if there is no error. And then based on that, we can correct the error and then read the message. All right. There are variations on the Hamming 7.4 code that increase the number of check bits but allow for more errors to be corrected. So what if we decided that correcting just one error isn't enough? We wanted to be able to correct more than one. We'll look at this next example next time. It's the Hadamard 32.6 code. Now, we're adding lots of check bits. We're only starting with 6 bits in the message. And we're blowing that up by a factor of 5. I mean, we're adding, 26 check bits to 6 message bits. But we can correct up to 7 errors for every single block. We're getting a lot more error correction, but we're also increasing the message size as well. Okay? Is there a way of deciding how much error correction you need? Well, if you know how noisy your channel is, if you know what the error rate is, there's a way to do this. So let's look at this example. Say we have a Hamming code that produces output of 33 bits, but it corrects 3 errors in every block. Okay? And for an individual bit, there's only a 95% chance that it's correctly transmitted. Every single bit has a 5% chance of being mangled. But these probabilities are independent. Every bit is transmitted independently from each other bit. What is the probability that a message transmitted using this code will be correctly received? So this ties into some combinatorics that you have had in the past. The message will be correctly received if there were 0 errors or 1 error or 2 errors or 3 errors. The possibility of 0 errors would be that there's a 95% chance of no error in an individual bit, but we have to hit that 95% chance all 33 times. The possibility of having no errors is 0.95 raised to the 33. They're independent, so we can multiply them together, and we have to multiply them 33 times for each bit. Or the possibility of having 1 error, or the probability of having 1 error, is getting the 95% chance 32 times and the 0.05 chance once. But this 1 bit that had an error could be in any of the 33 positions. 33 choose 1 position for that 1 error to show up. The possibility of having 2 errors is 0.95 to the 31. 31 correct bits and 2 bad bits. And those 2 bad bits can be anywhere in the 33. Any of the 33 choose 2 pairs of bits. And then you can see the pattern here. 3 errors will be 33 choose 3 for the bad errors. The good bits show up with a probability of 0.95, and the bad bits show up with a probability of 0.05. I don't need a 0 there. There you go. Cute. If you work this out, it is approximately 92%. Okay. And so, based on knowing how noisy our channel is, we can determine whether a 3 error correcting scheme is going to be enough. We have right here a 3 error correcting scheme, and each message gets transmitted correctly with only a 92% probability. Is an 8% error rate too high or too low, or not too low, but is it unacceptably high? Now, if it's unacceptably high, then we need to do more error correction than we've got. Okay? Or we need to find a better communication channel. That would be the other possibility. Anyway, this has been sort of a long-winded video today. I apologize for that. We will look at the Hadamard code next time. Take care.